Namaskar and welcome back to the course in statistical mechanics of phases and phase transitions. Today we'll start a new chapter on scaling and renormalization. And before we start this chapter, it's a good idea to take stock of where we are in the course. So we started by discussing systems with a large number of degrees of freedom which interact with each other. They can form separate phases, and these phases can be separated by phase transitions, and some of those phase transitions can be continuous phase transitions, and these continuous phase transitions have certain universal properties. So we constructed models and studied them, and we were able to describe phases using this idea of broken symmetry and an order parameter. We explored ways of solving various problems using perturbation theory using a small parameter, and we in the process also solved certain problems exactly and discovered the importance of spatial dimensions. We found that if you look at quantum statistical mechanics problems, there is a connection to a classical statistical mechanics problem for the ground state of the quantum statistical mechanics problem in one higher dimension. We learned about the concept of duality, which is a very important concept both for classical and quantum problems. We then went on to explore approximate non-perturbative methods. In particular, we looked at this thing called as the mean field theory, and the outcome of the study of mean field theory, at least in the simplest setting that we performed, was that the critical exponents that you get for continuous phase transitions are same irrespective of what is the symmetry and spatial dimension. So based on this, we thought we should explore certain other ways of doing the physics of statistical mechanics of these interacting systems, and this is a more phenomenological approach. So the idea would be to discuss the physics in terms of some certain emergent fields and some known phenomenology. And so the idea would be to produce some critical, so this is not opponents, it's exponents. They produce the same critical exponents as mean field theory, and these exponents also do not depend on symmetry and spatial dimensions. So we wanted to repair the Landau theory, and we said, okay, we need to include spatio-thermal fluctuations. So we wrote down something called as the Landau-Ginzburg theory, where spatial fluctuations are also and thermal fluctuations are also included. And we performed what is called as the saddle point Gaussian approximation. So you find the saddle point solution of the Landau-Ginzburg theory, and then you look at fluctuations up to quadratic order. That's why it's Gaussian. And what we find is that essentially you get the same critical exponents for most parameters except for the specificate exponent, which seems to depend on d. Yet with all that effort, we were not able to explain why you get different universality classes and why the exponents are different for different universality classes and so on. Despite the apparent failure of the Ginzburg-Landau saddle point approach, we were able to uncover many interesting physics ideas such as the Goldstone theorem, which says that if you break a continuous symmetry and your system has short range interactions, then you will produce a gapless state. You will have a state where excitations are gapless. We learned about the emergence of a length scale near a critical point, and this is called as the correlation length. And as you approach the critical point, this correlation length diverges. We learnt of power law correlations at the critical points, both from experiment and theory. These power law correlations are not following the power law given to us by dimensional analysis, and we find that there is something called the anomalous dimension. And so this is perhaps one of the most surprising aspects of critical phenomena, at least starting from some elementary perspective. And we went on to discover that if you have these Goldstone excitations, they will not allow you to have a broken symmetry state if the symmetry is continuous at finite temperatures in spatial dimensions less than or equal to 2. This is because the number of Goldstone modes at low energies is very large in low dimensions, and their fluctuations will contribute to wild fluctuations of the emergent field above the mean field value, which is the broken symmetry state, and it will completely destroy this broken symmetry state. And this is the famous Mermin-Wagner theorem, which says that you cannot break a continuous symmetry at finite temperatures in spatial dimensions less than or equal to 2. We then went on to uncover that there are associated with any symmetry and a class of Hamiltonians associated with that symmetry, there is a notion of an upper critical dimension and a lower critical dimension. So if you are above the upper critical dimensions, fluctuations are not very important. They contribute to some quantitative changes. They don't qualitatively change the physics. Whereas if you are below the lower critical dimension, then the fluctuations take over the story completely. And for example, you can have Mermin-Wagner like effects, and you can even not have broken symmetry states. And in between the upper and lower critical dimensions, fluctuations are there. They can't be neglected. They have effect at low energies, which is why the critical exponents are different from what is predicted by the Ginzburg-Landau saddle point approach. So these are some of the ideas that we have seen in the course so far, and the puzzles are not yet resolved. In fact, what the puzzles are is becoming more clear as we are exploring variety of things. So in particular, although we found a tool to calculate critical exponents such as Landau theory and so on, Landau-Ginzburg theory, we do not have the correct values of the critical exponents. And we certainly don't have any physical underpinnings of how different universality classes emerge and all of that stuff. So in this chapter, what we are going to do is we are going to sort of go back to experiments in a sense, and we are going to look at data, and we are going to make an important step forward by visiting the idea of what is called as the scaling hypothesis. So this is what we are going to do in this chapter. So it's a good idea to start by recalling what the critical exponents are exactly, in the sense more concretely what they are. So if you look at something like an Ising system in any dimension, let's say greater than or equal to 2, then you see that near the critical point, we know that the system, you need to tune two parameters, namely the reduced temperature little t and the dimensionless field. You have some field, a magnetic field which you can break symmetry, that has to be 0, as well as the dimensionless temperature little t has to be 0 to be at the critical point. So the definition of critical exponents now goes like this. So the specific heat exponent is defined as the specific heat diverging with some power of t, and the power is controlled by this exponent alpha. And there are these amplitudes on the left and right side of the transition, namely t less than 0 and t greater than 0. And similarly, there is an order parameter exponent. It tells you that the order parameter will grow as a function of distance to the transition of this reduced temperature by an exponent beta. The susceptibility goes like gamma, determined by exponent gamma. And if you are at the critical point, then we know that the system does not have linear response, and there is a nonlinear response which is actually characterized by this quantity delta, which is not 1, right. So that is what the delta exponent will tell you. So if you go back to our discussion just a moment back, we said that there is an emergent length scale called as the correlation length, and this correlation length diverges as you approach the transition. And this length scale C will diverge with an exponent nu. So there is a nu exponent associated with this correlation length. And finally, we have our famous anomalous dimension. So if you look at the correlation function at the critical point, dimensional analysis would have told you that it goes as 1 by r to the d minus 2. But you actually find in experiments that it does not go as d minus 2, it goes as d minus 2 plus something else. That something else is dimensionless number, which is called as the anomalous dimension. It is called eta. Now, if you simply Fourier transform this correlation function, so there is a conjugate momentum or wave vector variable which is called k. So, if you go to that language, you will see that this expression can be written as g of k goes as 1 by k to the 2 minus eta. So, this eta can be viewed either in physical real space, or you can also view it in the wave vector or momentum space. Okay. So, the upshot of this discussion is that associated with our usual critical point, we have 6 exponents alpha, beta, gamma, delta, nu and eta, which we have just revised here. We have revised their definitions in this slide. Okay. So, the idea is now, how do we understand these exponents and the relationship between them? So, let us visit this idea of scaling hypothesis. So, what is the starting point of scaling hypothesis? The scaling hypothesis is developed in the 1960s, and what was available at the time was a lot of experimental data on variety of systems, liquid gas, variety of magnetic systems, spin systems. There were a lot of data available at the time, and the data was of sufficiently high quality that you could make very clear conclusions about the idea of universality first and the notion of universality classes. So, what was observed is that you can have different universality classes. Say, for example, you can have the Heisenberg universality class, which is a continuous symmetry in 3 dimensions. You can have the Ising universality class, again a discrete, in contrast, a discrete symmetry in 3 dimensions, and they will have these alpha, beta, gamma exponents. Now, all say liquid gas and the Ising are in the same universality class in 3 dimensions, and there is a different universality class for the continuous Heisenberg spin, O3 spins. But remarkably, if you look at the alpha, beta, gamma, delta for these different symmetric classes in the same dimension, you will see that alpha plus 2 beta plus gamma is equal to 2. Both of these different universality classes will satisfy this equation. Similarly, if you take the Ising model in 2 dimensions and 3 dimensions and find out their alpha, beta, gamma, they will in different dimensions will also satisfy this same expression. So, what is it telling you? It is telling you that this alpha, beta, gamma are not independent, they are constrained by this equation. So, you may wonder, first of all, why should there be a constraint? Okay, so let us not ask why the constraint is there. We observe the constraint both from experiment and known theory. For example, we can solve the 2-dimensional Ising model exactly. So, what I would first invite you to do is you can, I have shown you tables of critical exponents of various systems in previous lectures, etc. You could pull those out and you could try to see whether this relationship is satisfied, and of course, they will be satisfied. You can check it for yourself. Maybe you can do that later. Okay. So, what is the puzzle here is that these exponents do not seem to be independent, and they satisfy such relationships which we now call today as scaling laws. They seem to satisfy what I call the scaling laws. So, you may wonder, why is this word scaling showing up here? We will see more about that in this lecture. So, what was also understood is that the critical exponents that are showing up are governed by the singular part of the free energy, right. So, we have seen, for example, when we studied Ising model and variety of problems, we saw that when we solve the problem, we will actually get some smooth part of the energy and some singular part of the energy, and it is the singular part, the one that gives you the non-analyticity of the free energy, that is what actually contributes to all this critical phenomena. So, the free energy density, roughly speaking, you can split into a smooth part which no one cares about, at least for the critical exponents, and the singular part which is governing the critical exponents. So, the scaling hypothesis is the following. The singular part of the free energy density is a generalized homogeneous function of its variables. Now, that certainly is a mouthful, and we may not all know about what you mean by generalized homogeneous function. So, what we will do first is, we will understand first qualitatively and then a little bit more quantitatively, what do we mean by a generalized homogeneous function. And hidden in this somewhat long-winded phraseology is generalized homogeneous function is the notion of scaling, right. So, we will first visit the idea of scaling in scaling hypothesis. What do you mean by scaling? So, let us understand the notion of scaling in very simple context of functions defined on the real line. So, you do not have to think about anything about thermodynamics or anything like this. You can just think about functions that you studied in calculus in say 10th standard and 12th standard and so on. Just think about simple real valued functions defined on the real line. Okay. So, I have this function g of x where x is a real variable. Now, what I am going to do is by the notion of scaling, what I am going to do is I am going to scale x. So, if x had units of let us say 1 meter, I am going to take 1 meter and make it 10 meters, or I could take 10 meters and make it 1 meter. So, I am scaling, I am actually stretching and pulling something like this. So, for this purpose I need a dimensionless quantity called a scale factor. So, if S is the symbol I am going to use to denote a scale factor. So, this is typically a number greater than 0, positive, right. We scale x by s, that means that I map x to sx, okay. So, I take this and I scale x. So, the natural question to ask is what happens to the function g after you scale, right. So, the way we would do this is if I want to know what is the value of g at some new position, at some position x in the new system, I will find out where this x came from. So, what will I do? I will, if you give me x which is the stretched variable now, the original variable which was at x is, its coordinate would have been x by s. So, this g tilde of x, the function in the new system, if you want to compute, you find out where this x came from. So, what you have to do is you have to divide it by s and take the value of the function, our original g, and assign it to the point x. So, this is how this function will change. Okay. So, now you can ask a question, is there some way I can think of this function g tilde being same as the original function? Of course, it literally cannot be the same, because you see, you can see that they have different arguments. So, they will not be the same. But the question is there a way to give some kind of equivalence between them? So, the way of giving equivalence between them is you try to see, can I stretch the value of the function by some power of the scale factor, right. So, here I am using this symbol mu, not to be confused with the chemical potential. So, if you look at the symbol mu, it is in an upright mu, whereas the chemical potential which we have used, it will be a sort of italicized mu. So, you should, whenever you see this upright mu, you are talking about an exponent rather than the chemical potential. So, please keep this in mind. So, what we are saying is that the function g tilde of the stretched variable, how can we check whether it is quote unquote same as the original function? So, the idea is the new function, if you stretch it by some value of this the stretch factor s, and then you claim that s to the power 1 by mu g tilde of x, if it is equal to g of x, then you will say that this function is scale invariant. So, how do I see this? So, g tilde of x is g of x by s. So, a function is scale invariant, or we will use the word homogeneous if there is some exponent mu such that s power 1 by mu g of x by s is my original function g of x. So, I stretch, I look at the value at the stretched place. If I can stretch the function by some power of the stretch factor and get back the original value, then I say that these two functions are equivalent, if you wish. or this function by itself is homogeneous. Okay, so here's an example. So I am writing down this function g of x is equal to 1 by square root of x, and I take this stretch factor s is equal to 2, right? And what do? I define g of x, that's the blue curve here, that's just 1 by square root of x, no surprise there. Now what I am plotting here in red is g of x by s, so that is s is 2 now, so it is x by 2. So you can see that x by 2 will be 0.5, so whatever was the value at 0.5 will be the value at 1, which is exactly what we want. But you see, the value at 1 of this quantity is now bigger than what it was before. So the functions are not equal. Now what I do is, I take this function and scale it by some exponent. So it turns out that the exponent here, this mu is minus 1/2. So that is 1 by square root s. And then you see that's the orange dash curve, that is this function, and I recover back my original g of x. Now this I did for s is equal to 2, but I invite you to check this can be done for any s greater than 0, right, and therefore will satisfy the condition of being homogeneous. So this kind of a transformation should be valid, this equality of s to the power 1 by mu g of x by s is equal to g of s must be valid for every s. There must be a mu such that this is valid for every s. This is the condition that we need for this function to be defined as a homogeneous function. So what is special about homogeneous functions? Okay, the speciality of homogeneous function is that they do not have an intrinsic scale. There is no natural scale in that function. So if you change the scale of your measurement, if you change the units of defining x, if you wish, that's what we are doing by stretching and moving, that's, you can make a meter into a centimeter or whatnot. The value of the function can be restored back to the original value by stretching by some power of the scale factor, and that power will be some exponent or what is called as the dimension of this homogeneous function. Okay, so the idea is that they don't have an intrinsic scale. So what would be a function which has an intrinsic scale? So here is an example of a non-scale invariant or non-homogeneous function. Take g of x is equal to e to the minus x by c, c is some length scale now if you wish, divided by x. Now you can convince yourself that there is no value of mu you can find such that this condition will be satisfied by this. The reason for that is, when I scale s, unless I am also allowed to scale c, which I am not allowed to, because I am only allowed to multiply this whole thing by s to the power something, therefore this function will not be scale invariant because it has an intrinsic scale. So scale invariant or homogeneous functions are functions which do not have an intrinsic scale. Okay, so what I invite you to do now is you can stop the video maybe for a minute and you can try to figure out some other examples of homogeneous functions. So what I am going to do is, I am going to talk about generalized homogeneous functions. So obviously that means that there is a special kind of homogeneous function which we have seen at least of one variable. So what we need, turns out, as we said, we need a slightly richer mathematical structure where we need to have homogeneous functions of more than one variable. Remember, the scaling hypothesis says that the singular part of free energy is a generalized homogeneous function of its arguments, namely, for example, in the Ising model will be t and h. So I have two variables there at least. So we need to discuss homogeneous functions of more than one variables. Okay, generalized homogeneous functions. So what is the definition of a generalized homogeneous function of more than one variable? So suppose I give you a function of n variables. This function is called a generalized homogeneous function if there exist exponents mu1, mu2, mu n such that if I scale each x1 by s to the power mu1, where s is the scale factor, so you see I'm not scaling all the variables by the same amount. Associated with each variable there is an exponent, and if you give me a scale factor, I will scale that variable by s to the power exponent. So for example, x2 will get scaled by s to the power mu2. So what is the statement? The statement is that this is a generalized homogeneous function if there are mu1, mu2, mu_n, such that for any s, if I evaluate this function, I can get back the original value of g of x1, x2, xn by scaling out s. So I just say that I can take s out of this, I take s inverse times this will give me back this function. So if I scale my variables with different powers of s, I can get back the original value by simply scaling out s in this fashion. So such a function is called a generalized homogeneous function. Okay. Now in the previous slide we have looked at simple homogeneous function of a single variable. Let's see what the generalized homogeneous function, how is that related to our previous example, say for example 1 by square root x that I gave you, right? So the idea of generalized homogeneous function, I just told you this, that if you scale these variables by certain powers, then you can restore the value of the function back by rescaling by s. Now let's see, suppose n equal to 1, that means I have a single variable, okay. So what is the definition of the generalized homogeneous function? So there exists a mu, right? So okay, there is a typo here. So this is not s1 mu, this is s to the power mu1, okay. So unfortunately this is proliferating here, right? So it's s to the power mu1. So there is this s to the power mu1, there is an exponent called as mu1, and so if I now differentiate with respect to s, when I take differentiate with respect to s to the power minus 1, I will get minus 1 times s to the power minus 2, this g remains as is, and when I differentiate with respect to s again, so I'll get mu1 s to the power mu1 minus 2, and this x1 will come here, that x1, and g prime, that's the derivative of this function g, and that will turn out to be 0 because the right hand side, because it's a homogeneous function, does not depend on s. So now if I evaluate this equation at s is equal to 1, then I will get this differential equation. It tells me that mu1 x1 g prime of x1 minus g of x1 equal to 0, which you can solve exactly, and you will see that g of x1 is some constant times x1 to the power 1 by mu1. So what is this telling you? It's telling you that if I have a generalized homogeneous function of a single variable, it has to be a power law, right? That's what it's saying. Okay, so this is the main result here. So again, you can see that this power law has no intrinsic scale. So if you scale the variable, if you rescale the function, you can get back this, you can restore back the function, right? So you can rescale the function to remove the effects of a scale transformation, right? So this is the idea. Okay, what happens if I have two variables? Just pause the video for a minute and think for yourself. I hope you got the answer. If you have two variables, you can simply take product of power laws associated with these variables, right? So I can take, for example, g of x1, g of x2 is some constant times x1 to the power 1 by 2 mu1 and x2 to the power 1 by 2 mu2. I'll leave it out to figure out why I'm writing it as 1 by 2 mu1 and mu2, and you will see that these will have exponents mu1 and mu2, right, based on our definition of generalized homogeneous function. So this is also a power law, as you can see, right? It's product of power law and therefore power law. But now you have to ask a question, are all generalized homogeneous functions simple power laws like this? And the answer turns out to be, right, so there's an exercise I just mentioned. The answer turns out that the generalized homogeneous functions of two variables are not necessarily simple power laws. So here's an example for you. Okay, you can, if you wish, you can pause the video and try to figure it out yourself, but here's the example. So you look at this function here. It is not a simple power law, right? It doesn't look like some product of powers and so on. So there are powers here, but there is a numerator, there is a denominator with different powers and so on. But this is a generalized homogeneous function, and I invite you to figure out what the mu1 and mu2 for these are, right? So bottom line is, whether you look at functions of this kind or functions of this kind or any other generalized homogeneous function, they do not have any intrinsic scales. So if you scale the variables with different powers of the scale factor, you can always remove the effect of the scale, such a scale transformation, by multiplying by S inverse and getting rid of it. So this is what we mean by a generalized homogeneous function. Okay, and this mathematical concept of a generalized homogeneous function is what the scientists of that era believed is behind the scaling hypothesis. So this takes me to the scaling hypothesis, which states that the singular part of the free energy density at the critical point is a generalized homogeneous function of its variables. So if we now look at the say Landau-Ginzburg theory or the Ising model on lattice or any of the variety of problems which we have looked at in the course so far, we know that the critical point can be approached by tuning two parameters, namely T and H, some symmetry breaking field and this reduced temperature T. So we know that the singular part of the free energy, I'm emphasizing we are only talking about the singular part of the free energy here, is denoted by a function f of T and H. So if you look at some other literature on this, they may put symbol Fs to say explicitly that it's singular part. I don't want to overload the notation here, that's why I'm using a simpler notation, but please don't think that this is the full free energy of the system. This is only the singular part of the free energy, and it's a function of T and H. Now, how do I put this fact that it's a generalized homogeneous function in a mathematical way here? So the scaling hypothesis can be put in a mathematical form by saying that this function f of th, namely the singular part of the free energy, it satisfies an equation of this kind: S inverse f of s to the power mu t t, s to the power mu h h is equal to f of th. Now what is the statement actually? The statement is that there are two exponents mu t and mu h such that this equation is satisfied for all s, right? Note that the scaling hypothesis does not tell you what is mu t and mu h. It only insists that such mu t and mu h exist. There is no way at this stage of the discussion to provide any values or bounds or any such thing for mu t, mu h. The hypothesis is that the function is of generalized homogeneous type and therefore there are mu t and mu h that exist. Okay, this is the hypothesis. Now you may wonder, like, what is going on here? Like, why would someone wake up on any day and try to say, oh, it's generalized homogeneous function? Why would someone do that? So there is a lot of work that went into formulating this idea. In fact, this hypothesis was worked on for many years and refined using all the available experimental data, all the available theoretical results, analytical results, and so on. So this is actually a result of working with experimental data and analytical results and so on, right? So this is the this was the outcome of a lot of such considerations. Okay, so you can ask, very good, you're making this hypothesis, so what's the big deal, right? Okay, so remember, you can choose S to be anything you want, let's say positive. So what I'm going to do is, I'm going to think of a system where t is less than 0. So let's say for being concrete, you can think of Ising model in 2 or 3 dimensions. Now I am allowed to choose anything S to be anything I want. So I in particular choose S to be mod t to the power minus 1 by mu t. So that's a positive number. And I take this expression and stick it into this expression. So what will I be able to get? I will be able to get the free energy density singular part as a function of t and h. I can show that that looks like this. So this is just s to the power minus 1 now written in the language of this definition of s. This here, because I am t less than 0, will turn out to be minus 1, you can check. And what shows up here is s to the power mu h, and s is simply this quantity, therefore it is just that thing times h. So what have I got for you? I have got a certain form of the free energy as a function of the reduced temperature, and this will allow me to make a certain statement now. So suppose I look at the specific heat. I know that the specific heat is the free energy, at least the specific heat exponent is defined in this fashion, the free energy in the absence of any external field. You take 2 derivatives of this with respect to this reduced temperature, that is approximately the specific heat. But if I put h is equal to 0, this quantity just goes to 0. So I have the free energy density is just f of minus 1 0 mod t to the power 1 by mu t. So I can simply carry out this differentiation 2 times, and you will see that this specific heat is proportional to t power 1 by mu t minus 2. That tells me that alpha, the specific heat exponent, is 2 minus 1 by mu t. So what the scaling hypothesis allowed me to do is to connect the scaling exponents mu t and mu h to my critical exponent that I am observing in experiments. So alpha is equal to 2 times 1 by mu t. Okay, we can do more. Now you remember that the order parameter is the first derivative of the free energy with respect to the magnetic field when the magnetic field is set to 0. So what do? Okay, there's a minus sign missing here, sorry, apologies for that. So m is equal to minus df by dh, and I take the derivative with respect to h, put h is equal to 0, and the notation here f01 means there is no derivative with respect to the first argument and there is one derivative with respect to the second argument. So in general in this literature, m1 m2 stands for m1 derivative with respect to the first argument and m2 derivative with respect to the second argument. Okay, so now you can just go through the algebra, it's very straightforward. You will see that it will pick up this mu h minus mu t here. So you will get this m goes as mod t to the 1 minus mu h by mu t, which tells me that beta is equal to 1 minus mu h by mu t. Okay, all right, we can do even more. I can go and compute the susceptibility, again the minus sign is missing, apologies. Susceptibility is minus d square by dh square f of th evaluated at h equal to 0, and all that will happen is you will pick up one more of mu h by mu t from the previous slide, and this becomes the second derivative with respect to the second argument and given by this. So that's some number times this quantity, which will give you gamma is equal to 2 mu h minus 1 by mu t. So what have you just discovered? You have discovered that alpha, beta and gamma are not independent if scaling hypothesis is valid, and this immediately tells us, you can just check yourself, it's very straightforward, alpha plus 2 beta plus gamma equal to 2. So I recover the scaling law which is obeyed by the critical exponents in different universality classes solely from the hypothesis that the free energy is a generalized homogeneous function of its variables. And this is valid for all symmetry classes in any spatial dimension, And this is a remarkable statement now. So, this fact that there is a scaling law naturally emerges from the scaling hypothesis. Okay. So, an exercise for you now is to work out the argument for t greater than 0 and obtain these amplitude ratios. So, I invite you to do that. That will be a very interesting exercise for you to do. So, what are the consequences of scaling hypothesis? So, we were away from the critical point. So, we were varying t in this whole discussion. What happens if you are at t equal to 0? Then you can do a different trick. So, what I will do is I will choose s going as h to the power minus 1 by mu h, and I will go through exactly the same machinery that I went through before. And now I will be able to write f of t h is equal to h to the power 1 by mu h and f of h to the power mu t by mu h times t and 1 here, because I have removed the h dependence, explicit dependence here, and brought it out by using the scale factor to be dependent on h. Now I can put t equal to 0 here, and therefore I will see that the free energy as a function of the magnetic field at the critical point is simply h to the power 1 by mu h f of 0 comma 1. Amazing result. And from here you can compute the magnetization, and the negative sign is here correctly now, right, at t equal to 0, and this gives us at the critical point. So you will end up getting m goes as h to the power 1 by mu h minus 1, which gives you that the critical exponent delta defined as 1 by delta is 1 by mu h minus 1. So what does this tell you? This tells you that you can relate delta also to mu t and mu h, and in fact that will constrain the alpha, beta, gamma are determined by this, and you will get a constraint between the critical exponents, and that constraint can certainly be written like this: gamma is equal to beta times delta minus 1. And this constraint or scaling law is obeyed by different, in all different universality classes will have different gamma, beta, delta, etc., but they will all obey this law if you wish. So I didn't go through the algebra of this derivation, so I invite you to do that, right? So what we have done is we have said alpha, beta, gamma, delta are related to mu t and mu h. So they are constrained. But remember, we had 6 exponents. There is also nu and eta. So a legitimate question for you to ask is, what happens to the other 2 exponents? Okay. So for doing the other 2 exponents, you can still go through the scaling hypothesis and generalize the scaling hypothesis to correlation functions, etc., but I will go through a slightly more heuristic way of doing this. So we know from experiments that away from the critical point, the correlation function does not do what dimensional analysis does. It does something slightly different, and it goes as 1 by k to the power 2 minus eta plus this correlation length zeta to the power minus 2 minus eta. We have seen this in the previous lecture. Okay, and we also know that the Fourier transform of the correlation function evaluated at 0 wave vector of momentum is the susceptibility. This is the Kubo formula actually, right? So we know that the susceptibility is g of k equal to g at k equal to 0, which means this is an exact relation, and it has nothing to do with critical phenomena per se. I mean, it's just a statement of the Kubo formula. Susceptibility will be proportional to correlation length to the power 2 minus eta. But we know that susceptibility is defined by an exponent gamma, and the correlation length c is defined by its own exponent nu. Therefore, because these two are proportional to each other, t to the power minus gamma will be proportional to t to the power minus nu times 2 minus eta. So that forces gamma to be equal to nu times 2 minus eta. That means, you see, somehow this nu and eta are also related to mu t and mu h, because gamma is related to mu t and mu h. So there is also some constraint here. But it does not fully constrain mu and eta. Mu and eta only one constraint in that you wish. So you can say one of them is independent, right? So this scaling law is called as the Fisher scaling law. Okay. Now, it turns out that over and above the scaling hypothesis, in many systems you can also come up with some additional statement called as a hyperscaling hypothesis. What is this hyperscaling hypothesis? This requires some experience to understand the physics behind this. I will briefly outline what the idea is. So, when you are in low dimensions, say below the upper critical dimensions, we know fluctuations are important. So, we know that the singular part of the free energy will be dominated by fluctuations. Remember all the discussion about Ginzburg length and all of that quantity. So, if you are within the Ginzburg length, for example, you will be dominated, everything will be dominated by fluctuations when you are below the upper critical dimension. So, there is a length scale that is there away from the critical point there, and that is C. So, the statement of hyperscaling hypothesis is that the free energy density in the dimensionless language will be determined by the correlation length, right. So, that is roughly the idea. That is, you look at roughly it is counting like the number of degrees of freedom, if you wish, within the correlation length. And what that will do for you is it will go as 1 by C to the power D. So, this is the hypothesis. It is called as the hyperscaling hypothesis. You can check this in variety of known systems and all, and if for example check in 2-dimensional Ising model, it will work just fine. So, it will be 1 by C to the D, and therefore, this F goes as T to the power D minus D times nu, where I have simply used the definition of the critical exponent associated with the correlation length. So, C goes as T to the power minus nu. I just put that in here, and therefore, I will get that the free energy scales like this as a function of T. But we know how the free energy scales with respect to mu T, for example, or we know how alpha is related to mu T. So, what we can do is we can relate d nu to mu T. So, take two derivatives of this, you will get alpha, and you can relate alpha to whatever you get from here, and you will end up getting what is called as the Josephson scaling law. So, this Josephson scaling law relating alpha and nu, the critical exponent associated with the correlation length, has a very interesting new feature which was not there in the other scaling law. The spatial dimension d explicitly appears in the scaling law. So, we know that the scaling law is valid only in systems where fluctuations dominate the singular part of the free energy. And for example, if you go to dimensions higher than or equal to 4, then this hyperscaling will not be true. So, this Josephson scaling law will be valid only in systems which satisfy the hyperscaling hypothesis. Certainly, many 3-dimensional systems will do that, right. So, as I mentioned, this is the only scaling law that depends on spatial dimension. Okay, so this is very interesting now. So, we have found 6 critical exponents. We know that there are 6 critical exponents associated with the kind of critical points we have studied, and we have 4 relations that constrain them. That means that among these 6 critical exponents, only 2 of them are independent, right. So, that is the outcome of the scaling hypothesis. The scaling hypothesis, including hyperscaling, etc., will tell you that there has to be these critical exponents are not independent from each other, and they have to satisfy relations which are coming from thermodynamic relationship. Like for example, specific heat is the second derivative of free energy, is a thermodynamic relationship. That does not matter what system you are dealing with. And it is those kind of thermodynamic relationships that are giving you the relationship between the critical exponents. So, once you make the scaling hypothesis, the rest is what is determined by physics, right. So, the scaling hypothesis is the central thing that tells us where the scaling laws come from. Okay, so let me summarize this lecture. So, we started off by saying that there are 6 critical exponents that describe the universal properties of a critical point. critical points of different systems can fall into distinct universality classes, and two different systems, like for example the liquid gas and the Ising model in 3 spatial dimensions, will fall in the same universality class, and they will have the same universal properties, namely these critical exponents will be same for both of these systems. The puzzle is that different universality classes, the critical exponents in them satisfy the same equations as constraints. So these are called as scaling laws, right? They satisfy the same relationships, irrespective of which universality class they are in. So to understand this, there was a proposal of what is now called as the scaling hypothesis, which states that the singular part of the free energy associated with this critical point is going to be determined as a generalized homogeneous function of the variables. So if you need to tune 2 parameters to get into to be at the critical point, this generalized homogeneous function will be a function of 2 variables. If you further make a statement about hyperscaling, which says that the free energy density is determined by the correlation length, so it will go as 1 by correlation length to the power spatial dimension, which is certainly not always true, particularly in higher dimensions. You can have all the constraints between the scaling laws derived, and they are the Rushbrooke equality, alpha plus 2 beta plus gamma equal to 2, the Widom, which tells you gamma is equal to beta times delta minus 1, Fisher, this is gamma equal to nu times 2 minus eta, and the Josephson scaling law, which depends on the spatial dimension, alpha is 2 minus d times nu. Okay. So what, okay, this is an error here. This is only 2 of the 6 effects, not only 4, it's only 2 of the 6 exponents are independent. It's not 4, this must be 2. And when you include hyperscaling, it will give you only 2 independent exponents. So what the scope of the scaling hypothesis is to show you where these kind of scaling relationships or the scaling laws come from. So scaling laws are you could say are a consequence of the fact that there is the free energy is a generalized homogeneous function of its variables. So there is a very natural question which is a puzzle. What justifies in saying that the singular part of the free energy is a generalized homogeneous function of its variables? There is no simple a priori justification for that, right? You make a bold hypothesis so that by making one hypothesis, you can understand all these, where all the scaling relationships come from. Let's say that in the scaling hypothesis, we also include hyperscaling. Then all these things are explained. But we don't know why this is the case and what is the reason for this. Okay. Perhaps from a more practical perspective, as I had emphasized while discussing the nature of the scaling hypothesis, I emphasized that mu t and mu h are not provided by the scaling hypothesis. So you could say that all the critical exponents alpha, beta, gamma, delta, nu and eta are determined by mu t and mu h of the scaling hypothesis, at least within the hyperscaling framework. Of course, you have to also give the spatial dimension, right? But it does not tell you what the values of mu t and mu h are. It just tells you that there exists real numbers mu t and mu h which will do this job. So this is a real puzzle now. So we have now understood where scaling laws come from. We still don't understand why there are different universality classes or a way to compute the critical exponents, or why is the free energy a generalized homogeneous function of its variables. Now, I am sure you will love to know the answer to this question. So please do join me for the next lecture where we will start discussing the notion of the renormalization group. So I'll see you in the next lecture. Thank you.